Today we are going to start the new video course, math course called Advanced Calculus. I will base it on this book right here. It's an out-of-print book that is done by a reputable author. Yeah. And I'm hoping that you can buy a copy of it. And you might think, how are you supposed to buy a copy when the thing is out of print? What happened is Amazon has recently decided to resurrect a whole bunch of dead books. Okay, they scanned it into the Kindle format and are selling it online quite cheap, actually. Not that this book was expensive before. Okay, this book is like this. Here's the information for it, and I want you to see the details of ISBN information, and also that you won't have any trouble finding one. So please find. I will also put a link to this book's Amazon page in the video description, so that you can. And they are selling it for like $10 or so, the Kindle version. And also, well, if you could get a hard copy, but I don't know how available that is. I was able to get one, and so I was lucky. But as time goes on, who knows? There are only so many hard copies available. So get a hard copy if you could, but otherwise get a Kindle copy so that you can follow in the class. Now, if it is not possible for you to get a copy of this book, you can still do this class, because what I'm going to do is that every single page of the book, I will show it to you on this video like this. Okay, every page I will show it to you like this. And so that you page by page as I go through the video, so that you won't have any trouble following in the book if anything is necessary. See, so then so if you can't get a hold of the book, you can still do the class, but without the book, it's more. You just have to go by video by video. Each video of mine, I will show you a little bit of the book, and I expect that I'll probably take 100 classes to get through this book. Now, the book is the Advanced Calculus is the math that's beyond calculus. Well, by its name, you can guess it. Now, this book has about 500 pages or so. Now, and the amount of time I think it will take will be the same amount of time that it took you to learn calculus 1, 2, and 3, which are also the prerequisite for this course. Okay, please make sure that you have studied calculus 1, 2, 3, and we're good at it. Okay, if you went through calculus 1, 2, and 3 but weren't that good, you need to do it again. I have finished the calculus video course online. They're all free, of course, including the book. Okay, because Openstax has published a bunch of free books. So and those calculus books, I'll also put the download links below this video in the video description, so that you can download them for reference if you ever need it, which I don't really expect you to need it that much. Because what advanced calculus does is it take most of the calculus concepts we learned in the past and then solidify it in a professional way. That is, whatever you were just glossing over before, now we're going to hit it hard, okay, like a real math student. Because back up to calculus 3, the math is taught in high school. It's also taught in the university level, but mostly it's done in high school, and it's taught in the university only because some high schools don't have the facilities to finish calculus or even to start it sometimes. So as a whole, however, up to calculus 3, you're talking about basic math. But this is the first class where we're talking about advanced, as in professional grade math. So that's why you need to be not just have had calculus, but you need to be good at it. However, as long as you were good at it, you don't have to remember every last bit of it, because we will revisit all those concepts and just hit it hard. The idea is that you have practiced enough so that you know how to hit math with a sledgehammer. Basically, is what we're going to be doing in this course. Now, today we are going to start with chapter 1, okay, 1.1, which is on page 1 of the book. Now, but before I show it to you, I want to remind you quickly of some differentiation rules. Chapter 1 is called differentiation, so I want to quickly talk about it. This is from the appendix of Calculus 1, 2, or 3. Okay, they all have it. This is Appendix B at the end of the book, where you get all the derivative formulas. I want to show it to you in case you haven't done calculus for a while and maybe a bit rusty on what these rules look like. So please pay attention to them and look them up if you can't remember, because you're going to need it for today's homework. Now, specifically, of course, pay attention to the product rule right here, the quotient rule, all the trigonometric functions rules, okay? How do you do derivative of the tangent, for example? The inverse trigonometric rules, those are not used as much, but they might show up sometime. And then, and most importantly, is in this homework that you will be doing a lot, is the exponential rule, specifically this one, Rule 23. Okay, where the derivative of a number b raised to the power x is equal to bx natural log of b. Okay, so it's the thing itself. It's like e, where the derivative becomes itself, except that there's a log that follows it. But so say if b is 2, b is a number, so if b is 2, then derivative of 2 to the power x is 2 to the power x itself, but times the number natural log of 2. So please look this up in any of the calculus books, or download one or all 3 of the calculus books, so that you can you can look at this stuff. All right. So here is page 1. Okay, let's see. Where's the page number? I don't see it. Well, doesn't matter. Here is page 1, and let's see. I need to figure out how to do this right. Okay, and then next. And here is page 2 and 3. I have it right here. Maybe a little closer. All right. And finally, this is the page 4 and 5, which includes the homework. That is the last page that we will cover today, if we get through it, that is. Let's see, I should put it a little closer so you have maximum angle. Yeah, does that look okay? All right. And finally, here are the answers for the first 6 sections, section 1 to 6. And yeah, and that's about it. All right. Another thing I should mention is that now that we're in the professional math classes, the expectation is for you to get a book, okay, that you need to read every inch and every line of the book, every dot and every comma. Okay, do not miss any of it. Read it slowly and make sure you understand every single sentence before you move on to the next sentence. And I will also approach teaching the book with the same goal, is that we're going to go through every inch of it and understand it and do all the examples, not necessarily to do all the homework, but we'll pick various homework that I consider necessary to help our understanding of the material. So I am totally expecting you to read the book extremely carefully. Okay, after you can do it before, during, or after the video, doesn't really matter. But the goal is that you absolutely must digest this book and well, not remembering everything necessarily, but go through it and understand it. And that's how we have fun, because as I mentioned in my title, this is a math as a hobby class, and I'm expecting you to study advanced math as a hobby, which can be done if we do it carefully and know everything, okay? And that is my expectation of you. So please be prepared to read the entire book, well, 1 page at a time, 1 sentence at a time. Don't be in a hurry. Do it slowly. So and repeat any part that you don't understand, and give it a big, strong hit. okay, until you can get yourself to understand as much as you possibly can manage. And of course, I'm here to help you do exactly that. All right, so having said that, let's look at the first page. Let's get started. How exciting, right? Advanced calculus is usually the first class that people study after they get past calculus, but it's not required. You can take other stuff too, which I will also teach in time. Right now, I'm just starting with the first one. And there are other college level classes like complex analysis, vector algebra, numerical analysis, and other stuff. I can't remember them all, but you can. All of those you are ready to do after you have a good solid experience in calculus, and you feel free to take those first if you want. So what's the difference? I don't know. It's probably better if you take this class first though, because then you repeat the concepts in calculus, except that now you're going to hit it with professional grade, okay, effort. So you might also wonder, how am I supposed to do professional grade stuff when I'm just doing this as a hobby? You can do it by going slowly, okay? It's like climbing Mount Everest one step at a time. You know, it'll take you quite a while, of course, but eventually you're going to get it. And well, Mount Everest without all the danger and stuff, and lack of oxygen and dying. We're just going to do this. Just to take this class at your own pace, and don't be in a hurry. It doesn't matter if it takes you a long time to get through. You're not in a hurry. This is just a hobby. All right. So having said that, let's look at page 1. Okay, now page 1, please read the book yourself as you follow along. Maybe take a screenshot of what I showed you of the book earlier if you don't have the book yourself. Hopefully you do have a copy of the book yourself so that you can follow it. Now first we are considering functions of several variables. In this section, we will call u equals to f of xy as the function, okay? And whereas x, y, and z are called independent variables. Those are things that change. And then u is the dependent variable. Sometimes we also use v, okay? Where u, it means that u is the result of f and xy doing stuff, right? To kick some number out. Now, we also consider multi-valued functions, such as like your book showed you. For example, this part right here, we have if you have a function like line 1, okay, you have a function like that, it can be decomposed into 2 chunks by the positive and negative square root, which is okay, and we'll consider that. Well, we'll consider that a function for now. Okay, it has you have 2 parts and it comes out with 2 answers. But you notice each part gives you a unique answer. But anyway, let's turn the page. Be sure you read the rest of page 1 carefully, like I said, and all the rest of the pages as we go along. Now, next we are going to consider partial derivatives. A partial derivative is where you take the derivative with respect to one of the variables while imagining that the other variables are just constants coming along for the ride. That is, you treat them as constants and nothing more. Okay, and pretend they are like, for example, if you have to take the partial derivative of f, let's say, and with respect to x, like this, then you're going to pretend that y and z in the formula as, say, 2 and 5, or something like that. Doesn't matter. Okay, they're just along for the ride. And similarly, you can also take partial derivatives with any other of the independent variables, such as y and z. Now we have the book has introduced maybe a new concept is you will take derivative with respect to the location. That is that what it says? Yep. For example, f2, the 2 down here means you take the partial derivative with respect to the second, the one in the second position. In this case, then it would be y, right? You're taking partial derivative with respect to y. And that way, if you change the names of your variables, nothing changes. You're still getting the same result. It's why you sometimes might want to do that. And So that is a new concept, but not particularly profound. And it's just the idea of if you see the number down there, that means you're taking derivative with respect to the variable in that location. And well, other than that, we will continue to take the derivative of something. And then of course, sometimes after you take the partial derivative, you will evaluate it at some set point that is x0, y0, z0. And then you just plug it in and something comes out, and that's that. So let's look at example A. Now example A, we have f of x equal to x to the power x and y. That looks pretty easy, right? Until you stare at it closer and you realize there's an x on top. Now, do you remember how to do that? Now, please do example A as part of your homework. In fact, in this class, please do all the examples that I present as part of your homework. That is, if I do it in my notebook and I show it to you, please do it yourself, which means you will do the example without looking at my results first. And then, and then after you're done, you can compare it to what I do, and of course what the book did, to see if you have any questions. And you should be able to learn everything from that as to how to do the example. And that's very important because that's the only way you can be, your understanding of the subject can be totally solid. Okay, you know it inside out. Okay, because we're at the point that it no longer matters if you're good at math. Okay, good at math is for high school. Right now, it's a matter of whether you get it or you don't. It's that simple. So let's look at example A. And when you first see that, you're like, why are there two x's? There's x on bottom and top. Do you remember how that was done? Well, that's taught in Calculus 1. And there's a trick to doing this type of differentiation. You have to do something called implicit differentiation and take the natural log. Okay. Now you notice that I'm writing the natural log as ln, but your book write down the log, log. And in the previous classes, you were taught that log stands for log of other bases, whereas ln stands for log base e. Now that is no longer true from this point forward. That is, that was true back in calculus, in the high school stuff. From this professional point forward, all log means ln only. We no longer care about any other bases. All right. So here we are. And having said that, we look at this stuff, and there's how we do the implicit differentiation. Please look that up if you don't remember how that is done. And then that's how we will calculate the derivative with respect to x, which end up being this thing, and then the derivative of y, which I believe is simpler. Okay, being that both the base and the exponent have variables in it that you're trying to differentiate. So that's how you do example 1. Now, so let's move on to example 2, and example B, which is a similar thing. Yeah, so please do example B as well, which you have different things. Why do I have so much stuff? Okay, the book didn't say much, but here's how you do it if you were to do it by hand. And so I think it's just you just basically take the partial derivatives, remembering all the rules. Remember the derivative rules I told you about in Appendix B in the calculus books that you can download. So please look at those if you feel rusty about any of the rules. And that's the end of example B. Now next, let's look at page 3. Please read the entire rest of the page too. Any part that I didn't really exactly mention, please read it yourself. Now, and make sure you understand it too. Now let's look at page 3. We have u plus this particular implicit equation. Implicit meaning that you have u in various places. Okay, that is, you don't have a u that has a direct expression of the rest of the stuff. So u is stuck in there in more than one spot, which makes it more difficult to calculate. Although nowadays the graphics calculators such as Desmos knows how to plot it, I think. If you type this thing in, it'll show you what the graph looks like. But we don't care about what the graph looks like right now. We just want to take the partial derivative. And to do that, we will do something called the implicit differentiation. If you can't, that is like the previous examples. If you can't remember exactly how that works, just look up the calculus book, or better yet, just Google it. Okay. Nowadays, the AI are very smart and can give you somewhat correct answers. By that, I mean the AI is often wrong by a little bit. They are about, I would say, in my experience, about 95% correct, depending on how tough the problem is. And what you do is but you should still look at them because once you see what they say, it will remind you of how it's done. And since you already know how it's done, it's just rusty. It's buried in deep storage of your mind. So once you see that, you'll be able to dig it right out and know how to do it. So the AI doesn't need to be 100% right. You, as a math student, will make sure that it is right. Okay. So anyway, that's the implicit differentiation. And then we have, well, what you do is just, pull off the implicit differentiation, which will give you some kind of a partial u partial x. But you notice that the thing has u itself in the answer, okay, which is okay. That is what we accept of implicit differentiation. And then, so that's that. Let's see, what is that? Let me see. Well, actually, the book is talking about certain previous examples as well. Well, it doesn't matter. Just go ahead and do all of them, okay? And which is what I did here. And you have different equations. Let's crank out the partial derivatives of whatever needs to be calculated. And then we'll call this done. Next, let's look at example C, where we have a system of equations where you need to calculate the partial derivatives. I don't know if you've ever done that in beginner's calculus, but the idea isn't particularly foreign. What you're going to do is that you take the partial derivative of each thing, and which will give you a system of equations for the partial derivatives. And then what you're going to do is use Cramer's rule to, crank it out, basically. And if you don't remember Cramer's rule, please look it up online. Or something, but here's how the name is spelled. Right here, Cramer's is spelled just like it sounds. But anyway, so using Cramer's rule of solving this is called simultaneous equations. You take the partial derivatives. Here's the Cramer's formula. Okay, you do this determinant thing, and then that will calculate this answer for you. And so please do that as part of your homework. And that's example C. Now, partial derivatives, of course, can go more than 1 degree. That is, you can take the partial derivative of some partial derivative, and it can even be mixed up. That is, the first one you might have partial u, partial y. Then the second time you can hit it with partial u, partial x. So that you have something like this. Those things are called mixed partial derivatives right here, and then they are not particularly. Well, okay, so here we have all these things, then and the way, notice the notation, okay? The way you do this is that the one that's on that end, the right side one, is done first. That is, to calculate this thing means that you take the partial with respect to y first, then x. So you're coming backwards, see? And then the way you denote it is, but the numbers are written a different way. That is, if you write it in numbers, it becomes F21. That is, you do 2 first, then 1. But the way you write it, you write down X and then Y. That's just the way it is, okay? And so we have all these different partial derivatives, and notice that it made a statement that a function of m independent variables will have m to the power n derivatives. But more importantly, they say that, of course, the partial derivatives, as you might remember, the mixed partial derivatives are interchangeable. That is, they're equal under most conditions. That is, fxy is the same as fyx, which makes them very fairly convenient. They're not that convenient. That you're still taking a bunch of partial derivatives. But here's the statement that your book makes. It says in the middle of the page, okay, in fact, the number of distinct derivatives of order n is the same as the number of terms in a homogeneous polynomial in m variables of degree n. That is, it equals to n plus m minus 1, choose n. Okay, which equals to that factorial equation that you see over here. Now, how do we know this? The way we know this is I dug out the relevant information so that you can prove this thing. Now, please take a screenshot of this this page if you need, if you don't remember how that is done, or if you just want to do it, and then probably doesn't hurt to think about it a little bit. Just I don't know, no reason. Now, the reason first, what is a homogeneous polynomial? That means some polynomial that's being made this way. Oh, like you have a bunch of k's, which is raised to some power, and then so that each polynomial its term has the same total degree. Okay, but the point is the number of distinct terms. That is, stuff gets combined together because the things with similar powers, you can add them up. Well, identical powers. The point is the total number of distinct terms is going to be this equation, as the book says. Okay, and remember what NCR stands for. The formula is given like this. And well, this is from probability, and you might or might not remember it. In fact, the way this, you might think, how would I prove that? That sounds a bit confusing. The trick to proving this thing is with something called the stars and bars theorem. Now, you might not even remember this at all. Now, if you don't, here's a very nice description of it that I cobbled this together from various websites, okay, that I think, even have an illustration. Right. So please study the stars and bars theorem and then figure out why this is the case, okay? But the number of distinct terms will be equal to that equation that we talk about. Now, I'm not going to talk about this in any kind of detail because the number of derivatives, partial derivatives, the total number of them is probably not that critical that I know of. But if it ever becomes important, then I will go for the stars and bars theorem. Now, for now, it's just something that's mentioned, so please look at the information I provided or dig it out yourself, either way, to figure out how to prove this thing. Like where the book get this. And let's now move on to example D and E. All right, so that would be in my book here. Now, I think they're just partial derivatives, right? Yeah, I think so. Example D and E, well, there looks like quite a bit of writing, but I don't think anything interesting is happening, okay? You just have to remember the derivative of the log, what are the rules, and then once you remember that, then you just take each partial derivatives, and then, oh, I see. The reason there's a bunch of writing is because we have to do the second partials and prove that they're the same or something. Yeah, so you have to do quite a bit of writing like I did here, but otherwise there's not much to it. Really, so please do example D and then example E as part of your homework. And with that, I believe we have come to the end of this section. Okay, now I'm at exercises on page 4. Now for homework, please do. Okay, here's the homework, which will also be listed at below in the video description below this video. The homework, please do problems 1, 3, 5, 8, and 10. And after you're done, I want to talk about all of them. Okay, starting in this class, I won't be skipping. If I assign you anything, I will talk about it. Otherwise, it's not worth assigning. So please do your homework, and when you're done, come back, and then we will talk about it a bit. So now that you're done with your homework, let's look at it. Now, okay. So problem number 1. Okay, let's look at problem number 1 a bit. Then you can see that it's just some sort of quick derivative. Yeah, and then you follow the rules. Make sure you follow all the rules exactly. The second one, the same thing, and where there's the chain rule, okay? Remember how the chain rule works. If you can't remember it, be sure to look it up. If you still have trouble remembering how it's done, just dig out a couple exercises, like online or in Calculus 1, 2, 3, 1. That is where this is taught. Do a couple of practices and they'll bring you right back up to speed. Anyway, or just do this, okay? Either way, the point is you absolutely must know how to do the basic differentiation, especially the chain rule, and especially when the chain rule looks complicated, like this one. So you have to first take, being the tangent is being squared, first you have to take this, take care of the square, and then you have to take the derivative of the tangent, and then you have to take the derivative of what's inside the secant. So each onion has to be peeled accordingly. Yeah, and so that's how problems 1 and 2, 1 and 3 are done. And then the answer, of course, I showed you the answer key, so you can double check to make sure we got it right. And because sometimes I will mess up too. Actually, I do mess up quite a bit. And so I try to double check and triple check everything, and I ask you to do the same. Now, when the answers are at the back of the book, that is, of course, tremendously helpful. If not, then we just have to double check and try to get the right answer if possible. Now, okay, problem number 5, we have systems of equation. So we will take the system and then apply the Cramer's rule, okay, and then and to find the determinant, which in this case happens to be a constant, which makes things somewhat easier. And then as a result, we can calculate the partial, whatever this is, yeah, and then you do the division, and everything should come out looking okay. Anyway, so that's that. And then next, let's look at problem number 8, which the answer is not at the back of the book, but the problem does look quite interesting, okay? And it challenges your understanding of, well, specifically the derivative of the exponent, because the exponent tends to be the most difficult or the most odd-looking thing in differentiation. So here is problem number 8. Here's x, which is to the power y, which is to the power z. Okay. Now to do that, what you're gonna do, and well, first you take derivative with respect to x. What you do, as always, is that you pretend that y and z are numbers. Like let's say y equal to 2 and z equal to, I don't know, 5 or something. And then so it's just x to the power of some numbers. So you use the standard power rule, which means you take down what's on top, y to the power z. That's not a 2 there, that's just a z. And then x to the power y to the power z minus 1. Okay, that would be the first answer. Now the second answer, let's see, it might be, gets more confusing. Well, the way you deal with it is write a sample here, okay? Pretend that now the x is the constant, and then y is some variable, and then z is yet another constant. So that's, so if you look at that, that makes it a little easier. So what is that? That is the same as this formula right here. dB to the power x by dx, which goes by this rule. And then whereas the x, now y to the power 3 is the new x, okay? And so it's, again, we're using a chain rule to, we'll peel this onion one chunk at a time. But so what we're gonna do is partial y would be, would equal to well, the answer being this, okay? It will be equal to the natural log of the base, right? And then the exponent itself, you copy the whole thing down, and then the derivative of the exponent. The exponent is y to the power 3, so, or y to the power z, so it becomes zy z minus 1 by applying the power rule. So that's the second one. And finally, the third object is, we're still going to do it the same way. Okay, now we have, now this time we're going to pretend that it's 4 to the power 3, which itself is to the power z. And the way to do that, we are going to use this thing again. Okay, and this time we pretend 3 to the power z is a new x up there, and apply that thing by itself. So the answer will be natural log of x, and then the thing itself which is x to the power y to the power z, and then derivative of 3 to the power z, which means you have to apply this rule again, okay, which is the natural log of y, and then y to the power z, because this time z is just z itself, so there's no more. We have come to the end of the chain, and that should be the correct answer. All right, so finally we are going to do, am I done with this? I guess I am, or something. Well, whatever. Let me check. Okay, finally, let's look at problem number 10. I guess it's done. Well, the answer in the problem 10 only gave you one part of the 4-part answer, which is good enough. Okay, we'll accept what we can get. And the book is copyright back in what, 1948? For heaven's sake, that's like, which means the author would be something like 100 years old, maybe 120 or something by now. Yeah, so anyway, and so this book should be going into public domain soon, seriously. And anyway, the point is, so back then they're not very considerate. Okay, they just they give you one answer, and then you need to be thankful that you got even 1 out of 4. Anyway, so we have problem number 10. So here's how I worked it out. The part that they gave the right answer to is this one, which turns out to be, I got it right. I don't know about the rest. I hope that that's right too. But anyway, so we will do it like we always do, okay, which gives us ux, uy, and then from this equation we got vx and vy, okay, and that should be correct. And then and that marks the end of this section. Oh no, I wore the wrong shirt for this shirt. I mean, I was supposed to have my Star Wars shirt. I was even looking forward to it, but in the excitement of starting a new course, I forgot this part. You know, I was focusing on the book and all that stuff. So, but I'll be sure to put this as the screen, the video, what do you call it, title page or something, so that this shirt will show up on the first page. But and that's why I'm wearing the wrong shirt. I'm still wearing the Calculus 3 shirt when I was supposed to be wearing this. So, but I won't make this mistake again. Okay.